Alright, hello, welcome everyone. So today we're going to talk about this similarity solution. Okay, we're going to continue this and just want you to know one thing. Just want to give credit. I think this similarity solution was first thought of by Paul Hausen, I think, based on one of these books. I think the similarity solution is first developed by Paul Hausen, I think. If that's how to pronounce his name correctly, I'm not really sure. Okay, but so we want to continue solving this. So first we'll need, we have reduced our energy equation to this very simple form with just a theta double prime, a Prandtl number, f and theta prime. Okay, so how are we going to solve it? Okay, we don't need numerical solutions as like we thought of the last time, and also f eta, right? F eta is how do you say? F eta is already known based on the similarity solution from the Blazier's flow. Okay, the standard Blazier's flow. Okay, so that's fine. That makes it a bit easier. Okay, so and if you want to get our heat flux, where do we get our heat flux from? We go by this. Okay, I think del T del Y. Yes, this is the rough kind of this is roughly what you want to go for. Del theta del Y is also del T del Y. Of course, you kind of have to adjust the gradient a little bit, and of course you have to change the right hand side to fit the actual profile. So what is that profile? We first have to find that. To find the temperature profile first, we need two boundary conditions. So two BCs. Okay, two boundary conditions. Okay, because this is a second order linear ODE. Okay, linear ODE. Of course, there's this f down here, which is a known function of eta. So that's not really a problem. It doesn't really depend on this theta double prime. Okay, so that one don't have to worry too much. Okay, so what's the boundary condition when y goes to infinity? Y goes to infinity. Okay, y goes to infinity. What happens? T goes to what? T infinity. All right. So from this boundary condition, what can we get? What can we infer? Okay, from this boundary condition, we will just change it to, eta is actually y. There's a as y goes to infinity, eta will go to infinity as well. So we can write eta goes to infinity. So as the similarity variable goes to infinity. Okay, so what does the dimensionless temperature go to? This dimensionless temperature goes to 1. Okay, theta goes to 1. Why? Because dimensionless temperature is actually let's see. Okay, dimensionless temperature just off the bat is actually T minus Ts over T infinity minus Ts. So Ts minus T infinity over Ts minus T infinity, that's 1. Okay, so reminder, theta equals to fraction T minus Ts over T infinity minus Ts. If both the numerator and denominator is the same, then you just get 1. Okay, for any finite number. Right. Okay, so what do we have next? We will need to consider the temperature at the surface. So what's the other boundary condition? Y equals to 0, then T equals to Ts. So that means, okay, eta equals 0, theta equals 0. Alright, theta equals to 0 because ts minus ts is just 0. So these are your two boundary conditions. Okay, so let's solving the equation. Okay, and let's give it one more space here. Let's solve the equation. So again, we'll just use the same thing, and now want to write it in this form so that it's very obvious what you can do. Okay, partial eta. Okay, partial by partial eta of theta prime equals this. Now, or rather, let's do it this way. And then what can we do? We can just separate the variables. We'll just bring it to the other side. Of course, you can integrate already here. You can start integrating the equation as like this form. I mean, you have to divide throughout by theta prime first. Okay, so we'll just do that. So 1 over theta prime, I'm going to divide throughout by that. Okay, let's divide throughout by that. 1 over theta prime. And let's go. Then we'll just integrate throughout by eta. Okay, integrate throughout by eta. So integrate from, so where do we integrate eta from? We integrate over the whole domain from 0 to infinity. 0 to infinity. Okay. Okay, the eta. And we'll just do the same thing for the other side. So we have f, okay, pr and f, and the eta. Okay, so this one pretty simple. We just do our boundary condition switching. Yeah, but this means we need a theta prime boundary condition, which we don't have at the moment. Okay, but yes, what can we say about this equation? Yeah, maybe you don't want to. Yeah, I'll just leave it as such. Okay, let the etas cancel out. Okay, we need the theta prime boundary conditions as well. So so the theta prime at, okay, eta equals infinity. We don't know what that is, and theta prime at eta equals 0. I mean, that's how you would do it in theory, but you'll make one big mess. Okay, but essentially you'll get some logarithm looking thing. You get some logarithm looking thing. Oh, sorry, I should put eta equals 0. Okay, let's just do that. Just do eta equals 0. You'll get a nice logarithm. This thing we'll just kind of like leave it there. This will be f of eta. Just so you know, we'll have the integral of f eta. And of course, Prandtl number may or may not change over the whole fluid, so we don't really know that. Okay, so this will easily reduce to a logarithm. And then what happens is that we will just integrate the whole thing through one more time. Okay, so let's put that down. I'll just put log base e, and I'll do a fraction here of this will go to the bottom, this will go to the top, and there we go. You just have a simple logarithm here, nothing really spectacular. Okay, so yeah, so we can just do the exponential thing and just do the exponential thing, exp of all of this. So we'll have a fraction. All right. Okay. Well, this is one way of doing the equation for sure, but okay, maybe I should not have integrated it as such. But let's put it this way. What if, I mean, this is not very helpful. Eta is not infinity. All right. So we will do the same integration, like so. Kind of give you the idea. Of what we should be doing. We should be doing something like that. Yes, now this makes more sense. Why is there still infinity there? Oh, eta equals eta becomes at the bottom. It should be at the top. Right, there you go. Finally. Alright. Okay, so not too bad. That will just mean that yeah, and basically over here you'll need to make this change this into some sort of dummy variable. So I can just put eta prime down there, no problem. Okay, Prandtl number, I will just leave it in there first. Though technically speaking, in our simplifying assumptions, we can take the Prandtl number out. Yeah. Okay, so we'll just do the we'll just do this exponential form. And we'll just put eta equals to eta. Okay, and of course eta prime, yeah, would be the operative variable, the dummy variable, I like to call it dummy variable. Okay. Now, okay, quite simple. Oh, you should not have infinity there, eta. And then you have eta prime. Nothing too difficult there. Okay, so now what? Okay, we can bring this term to the other side, and then it'll just be a first order. It's a very simple calculus problem after that. Okay, this part here is a constant. And this one here is just theta prime at eta. Okay, some people like to use the dummy variable beta over here. It's kind of the same, doesn't really matter. Okay, so this one is just evaluated at eta, theta prime evaluated at eta. Okay, theta prime evaluated at eta. Of course, then what we do now, we integrate again. Okay, same idea. To get our temperature profile, integrate again. Okay. Integrate from 0 to eta theta prime okay, the prime, the eta prime, same idea. Then the right hand side we are also integrating again. Integrate from 0 to eta. The eta prime. And this will then be our very nasty looking solution, where the left hand side just reduces to theta at eta. Okay, theta at eta. Theta evaluated at eta. The rest of it, well, it's kind of left alone. Now this part is where you probably need some numerical solution. I am not sure what kind of solver you kind of want to use. Okay. Anyhow, probably we might not want to use eta prime twice, because this will be superbly confusing. Let's use another dummy variable. Okay. In textbooks, you will probably see dummy variables like beta being used. Okay, beta and gamma. So let's just use use other text conventional dummy variables to avoid confusion. Alright, so let's avoid some confusion. So the eta prime is over here. We'll use gamma for the outer integral. So gamma equals to eta, and then gamma equals to 0. That's the integral limits. And for the inner integral here, in the exponential bit, we just use beta, because anyway, that's what you'll see in textbooks anyway. So so that's from Bijan's textbook. It uses this kind of a thing. So I use beta as the dummy variable. Okay, beta. Oh, beta and eta are just like one letter of difference. I just realized. Oh, discovery of the day. Okay. Now hopefully this is a little bit clearer what's going on. This beta equals 0 to beta equals eta. This one is just the integral of this dimensionless stream function here. Nothing too much to worry about. Then this integral here is just for the rest of this whole thing, because we just integrated out. Yeah, we integrated out this part. So you get a dimensionless temperature. Okay. One problem though. We don't know what this we don't know what theta prime at eta equals 0 is. Okay. Okay, so what do we do? We set this equation. Okay, we set this equation. And we take the limit. The second round of integrals, right? We take the limit of. We use the boundary condition. Okay, what's the other boundary condition? Which is that one is theta equals to 1 at eta goes to infinity, right? Oh, okay, eta equals to, wait, hold on, let's go back. I can't remember. Oopsie. Okay, eta equals 0 when theta equals to 0. Theta equals to 1 when eta goes to infinity. Okay, so I remembered correctly. Not too bad. Okay, almost at 20 minutes. So I'll just okay, equal infinity. Okay. So let's do this. We'll use this for the dummy variable, and the dummy variable representing eta is what? Okay, the dummy variable representing eta is gamma. Okay, so we'll do the gamma bit. Okay, so this is gamma, so we'll just shoot eta equals to infinity here, and of course gamma goes to infinity. All right. Ooh, that's a quite a handful there. All right. So now, what happens? Okay, we'll need to do a few things. First, we notice that this is equals to 1, right? As prescribed by our boundary condition. And the other thing we note is that theta prime and eta prime equals 0. Okay, theta prime. Oh, what? Did I use eta prime again? Oh shucks, I should use beta. Or eta equals 0. That's fine. Having so many dummy variables is pretty confusing. Okay. So anyway, here we can just put eta equals 0 because that's a standard boundary condition. I'm not going to put eta prime equals 0 anymore. Here, and one more here. I mean, it's more or less the same thing, okay? It's more or less the same thing, but yeah, this one is a bit easier and clearer to understand without all the dummy variables going in. So okay, I'll just use this. Know that eta, gamma, and beta are kind of interchangeable because it's just the proper nomenclature to do this kind of integration. Okay, so yeah, we note that this factor is actually constant, so we can bring it out of the integral, no problem. It doesn't affect anything. So we can actually bring it out, and I'll bring it to the other side. Okay, I'll give it the power minus 1. Okay, so okay, let's do it this way. Yeah, theta prime at 0 to the power minus 1. Okay, because that's a easier way. Okay, and this is our value, okay, of theta prime 0. Of course, I need to bring the minus 1 to the other side to make it complete. Right, square bracket, and I'll put left square bracket, and this will be, yeah, forgot this, closing parentheses. Right. Great. Opening parentheses. Alright, there you go. There we go. And this should be numerically solvable depending on where eta is. So this has to be integral. We will integrate it to wherever eta is. And the rest will be like, just integrate it to infinity based on this gamma. Okay? If you want to be even more clear, I think this beta should be changed to gamma so that you can so-called mathematically using correct mathematical symbols. Alright, I think the beta should not be equals to eta. You should change it to like gamma or something. So that's the thing about dummy variables. So alright, so that you will have a function based on gamma on the inside, and then you integrate that from 0 to infinity. Oh, what a mouthful. Okay, so this is the correct solution. So where again theta and eta is this. Okay, so the dummy variables are a little bit, annoying, confusing, whatever. Okay, let's do this theta prime 0. And integrate up to gamma. Yes, okay, now we are in business. Okay, so next time you can just substitute this thing in here, you'll be okay. Of course, we can bring the theta prime out just for clarity, if I'm not wrong. I think better not. I'll leave it inside. Okay. Wait, no, this is actually constant. This is actually constant, yes. Yeah, I can just bring it out, no problem. Okay. Anyway, is it constant with eta? Don't think so. Sorry, I think I made a mistake there. Made a mistake there. Okay. If I come to think of it, if this is the, this will be integrated and it'll be a constant. Okay, so this doesn't actually change with eta because none of the things in here actually depend on eta. Okay. Because once you have the first integral, you will get exponential to a gamma, and once you get that exponential, you just integrate it out from 0 to infinity. So this actually here will be a constant. Yeah, that was correct. Alright, and now we have a final solution for this thing. Of course, you can actually bring the Prandtl number out now. So you just do that. Okay, bring the Prandtl number out. Again, the solution here may differ by a factor of 2 or half or whatever, depending on how you initially define your similarity variable. But the concept, again, is more or less the same. Okay, so this is the solution for the dimensionless temperature profile. Okay, it's in a very, very weird form, very messy form. It's not like you can punch this into a calculator and expect something, but if you were to use MATLAB or something else, I believe this is actually doable. Okay, MATLAB or Python. Okay, it's a simple integral, of course depending on the Prandtl number, and you can actually plot charts and graphs out of this, so long as you know what f is. Okay. Okay, wow, we are at 30 minutes already. How time flies. Okay, I'm gonna stop for now, and I guess I'll see you guys next time. Okay, we're going to discuss very simplified solutions to this funny looking thing magic here. Alright. Okay, so thank you. I'll see you guys again. Bye bye.